Okay, so let me thank the organizers for giving me a chance to speak here. The work that I'm going to present is joint work with Andreas Adolfsson, Tathagata Mukherjee, and Eduardo Pesiliao. It is about large-scale localization when you are only allowed to use received signal strength. So we're looking at the problem of positioning like the last talk, but we're not shooting guns. We're just using an RTLSDR to try to figure out where we are on the planet or in the country. And we are just restricting ourselves to FM transmitters. So you're just allowed to look at the received signal strength of FM transmitters and figure out where you are in the country, for example. This map that you're looking at is there are roughly 20,000 FM transmitters in the United States, and this map actually shows you what is the number of transmitters you can view at every point in the country. So it varies from 0 to 100 because there are 100 channels. And if you had a better antenna, then you could listen to much more than a few radio stations at one position. So if you had an antenna that could listen to 40 dBu signals, then you could get to a lot of music in the entire country, actually. So the problem we are looking at is, again, trying to figure out where you are, like in the last talk, but except that we're not shooting. So we're looking at anywhere where you are allowed to collect some part of the spectrum, and then you're trying to figure out where you are. This has applications to many different other problems, like many of the talks that have been here already. Okay, so sometime back there was a study of the trade-offs between what you can listen to and what are the pros and cons of studying those problems. So for example, if you could look at Wi-Fi spectrum and then try to localize yourself where you are in the country, there are some pros and cons of doing that. And the same thing applies to FM transmitters as well. So we are looking at the FM outdoor problem here, where we're looking at the FM transmitters that are outdoors. And the accuracy for that is typically known to be low. The coverage is high, the power consumption is low, and the cost of infrastructure is also low for this problem. Okay, so what does an FM transmission look like when you're looking at signal strength? And this is image for that. So this is a 90.5 megahertz transmitters in San Jose, and you're looking at the 60 dBu polygon for that particular transmitter. And on the left, or on the right, you're looking at, this table is actually showing you how many transmitters, what's the range of the different transmitters in the United States. So if there are roughly 20,000 transmitters, some have an average range of, say, 10 miles, and some have a large range. And it's actually showing a histogram of all the transmitters and what their ranges are. Okay, so if you're looking at RF-based localization techniques, there are many techniques you can use for localization when you're trying to do passive localization. You can do beacons, and you can do anchor-based or angle of arrival or time reference of arrival. In this work, we are just trying to push the limits of what you can do with received signal strength, and which is very noisy. So you can, even sitting here, if I record FM signal strength, more than likely after 10 minutes, I'll get a 5 dBu or 5 dBm difference from what I received 5 minutes earlier. So it keeps on varying as time passes by. So in this project, we are looking at using the RTLSDR to do the localization, and we are looking at something very scalable, so preferably something like a country. We are using the US as our test bed in some sense for this work. And the algorithm that I'm going to show you is pretty simple and scalable. It can be hopefully used for both indoors and outdoor localization, and it's also easy to make it distributed. So if you had multiple receivers, then you can easily incorporate that into this algorithm. And it does not need line of sight, and it does not need sync. So all of these hard problems we are avoiding by using just learning and algorithmic techniques. Okay, so before you get into localization, you need some test data. And we gathered this test data by doing something very simple. So we put an RTLSDR on top. So we put an antenna that comes with the RTLSDR on top of a car. and then we just hooked it inside the car using a laptop, and we drove roughly 350 miles on the road, and we collected 1,000 samples that we will use to actually test where you are. So, and this is again assuming, so when we are recording the test data, we are also recording GPS location, because then we want to compare how accurate you were when you actually computed the position from the algorithm. You don't need an introduction to RTLSDR, and there have been many talks here that actually used RTLSDR already. And this is what we actually gather from the RTLSDR. So we use power and frequency diagrams. So you have 20 megahertz range on which we are actually computing power. So we are just looking at, this slide is for some reason cut, but you're looking at, so for each frequency, you're looking at what power you are receiving using the RTLSDR, which is kind of a rough estimate of power. It's not a very precise estimate of power. Okay, so if you look at this slide, the top part is what you get from RTLSDR. So this blue piece is what you're getting using the RTLSDR. And the bottom piece comes out of two different things. So one is a calibration of the RTLSDR that I'll talk about in a second. And the other is a simulation system that we created that gives you the actual power versus frequency diagram in the entire US. So, and that comes from a phase that we use, which is called map generation. So the map generation part actually comes up with this power versus frequency diagram over the entire US. And the blue spectrum is what we record when we go somewhere. And what we do is we calibrate the blue signal to the simulation, and then we measure and correlate in some sense. So this is the base of the algorithm. I'll tell you a little bit. So let me go into these phases that we do. So the first phase is map generation, which generates the map of the entire US with these diagrams. And the query phase is the one where you record using an RTLSDR this power versus frequency diagram. And then you find peaks, you do a subset filtering, and then you do a nearest neighbor to find where you are. And I'll go through this in a second. So let me show you what the map generation phase does. It takes the entire country and it breaks it down into 2.4 mile by 2.4 mile blocks. And in each block, now we are trying to figure out for each of these FM frequencies how much power I'm going to receive. And that we can compute using the data that we have from the FM transmitters and the 60 dBu polygons that are associated with these FM transmitters. So this is the algorithm that drives it, and we have to also be careful of time, because you're doing this for the entire United States, and we are running this on a single PC, which is 8 cores. So you have to be fast enough to be able to do this for the entire country. I won't go into the details of the algorithm, but it's kind of simple. So this is the output of the algorithm. So what it does is it takes this polygon that I just showed you for the 90.5 megahertz transmitter in San Jose, and it makes sure that the 60 dBu polygon is part of the data set, so is a part of the transmission system that you're trying to get to. So in theory, it should be all spherical and nice functions, but in reality, they are not. And you can see that these functions are far from spherical or some simple shape. So this piece is, so once this function is computed using this algorithm, this is for one particular frequency. We do this for all the 100 different frequencies, and then we do this for all the 2.4 mile by 2.4 mile blocks for all the 20,000 stations that we have. So this is some amount of computation that we have to do, and it takes around 2-3 days to compute this whole simulation structure. Once you have this simulation structure, then you can now record using an RTLSDR the frequency versus power diagram, and then try to figure out where you are in the simulation system. And the first step of doing that is trying to do peak finding. So the first thing we do is we try to figure out where these stations are, and that's easy to do by running a peak finder. And here I'm showing you some of the spikes that the peak finder finds so that it can be used for localization. So it can be used for finding out where you are. Once the peak detection is done, then there is another phase that we run, which is called the subset filtering phase, where what we do is we use a very simple observation that if you're looking at, so if you're in San Diego and you're looking at 99.3 and 99.7, and these are the transmitters that are near you, then any of the 2.4 mile by 2.4 mile boxes that you're looking at, if they don't have both of these transmissions, then they're useless. You can throw them away. So the only boxes that you're really interested in are the ones that have both 99.3 and 99.7. And that you already know because you just used your RTLSDR to figure out that these two frequencies are in there in the peaks. So this step actually filters out most of the blocks in the country by just using this observation. We call it the subset filtering phase. And there is a nice way of implementing this fast that I won't go into, but you can optimize the queries on these boxes and find them very fast. So which are the boxes which have all of these peaks in there? Okay, so once you've found the peaks, then that's all the algorithm is, and this is the complete algorithm. So what we do is first we acquire the RTL power versus frequency diagram. Then we detect the peaks in step 3. And step 4 is the subset filter, which filters a bunch of boxes in the country that are candidates for being an answer. And the last piece does a Euclidean nearest neighbor. And so in Euclidean nearest neighbor, what we do is we look at the calibrated version of the RTLSDR frequency versus power diagram. And we look at, in these boxes that are still candidates, what the frequency versus power diagrams look like. And we look at the Euclidean distance between them, restricted to only the peaks found by the peak detector. And we find the one that's nearest, and we say this is your location. So that's all this algorithm does. And this algorithm does not take care of anything like what time you are measuring it, or what temperature is there, what humidity is there. And all of this actually changes your received signal strength. So this is a diagram which shows you that even on one place, the received signal strength can vary a lot when you're doing it using an RTLSDR. So one of the things that was also interesting is that you can show that if you assume that this curve is Gaussian, then there is a way to prove that the Euclidean nearest neighbor is actually one of the optimal ways of doing what we are doing, so finding the location. And there's some math behind it that I'll skip. But the assumption that there's a thin Gaussian actually helps you to do Euclidean nearest neighbor for these problems. Okay, we also tried other approaches like Fry's model, if you've heard of it, to try to do this. And it turned out that the error was much higher than the Fry's model compared to what we were doing. 10 years ago, there was another study similar to this, which was doing this using just a city. So in the city of Seattle, there was a bunch of researchers that did something similar. And they were using Kendall-Tau distance instead of Euclidean distance. And it turns out that if you use Kendall-Tau distance, the error blows up when you start to get large scale. And the other thing I should mention is that, okay, so all of the data points that we've gathered so far are on the road. So there's a lot of multipath and things like that going on the road. And we've not explicitly taken care of all of those in our algorithm. And still, the average error we can get on the road is roughly 5 miles. And we can get, so another interesting thing I should point out is that if you use better calibration, then you can get from 5 miles to 3.5 miles already on the ground. And when I say better calibration, it means that you have to throw in learning tools like random forests or neural networks on the calibration instead of just using the linear calibration that we use right now. Okay, so this was on the road, and then we started wondering what happens in the air. What happens if we try to do this in the air? So let me show you a small video of, if I can play it. Okay, so probably the sound will not play. Okay, so let me skip the sound and maybe I'll, is it playing? Yes. Okay, so we built a small drone system which can actually go, so we wanted to measure things at 120 meters or something higher. And what we did was we built a small drone from off-the-shelf parts. So we basically bought a DJI S1000 frame and motor and ESCs, and we put a Pig's Hawk system on it, which is the autopilot, and then we put an Intel i7 box on it that controls the Pig's Hawk. And then we made it autonomous so that it can go up and it can record using the RTLSDR or the B210. So it has both B210 and RTLSDR on it. And it can record the FM spectrum. So let me show you. So this is the FM spectrum it recorded at 120 meters. And we made it autonomous in the sense that you can just flip a switch and it goes, does its experiments, comes down, and then you can pull out the data. And then you can figure out where in the air you are in the country. So that's what we were trying to do. OK, so this is the details of the autonomous data collection system that we built. And these are the 30 places where we did these experiments on. So in Tallahassee, Florida, where I'm from, we put this drone, and then we just ran these experiments 30 times. So what this drone does is it just checks the GPS accuracy and then collects RSI data on the ground and lifts itself to 120 meters, and then again remains stationary at 120 meters till it gets the data, and then it lands automatically. And then we want to run data processing on it. So we want to know how accurate can you get as far as positioning is concerned if you look at that data which is collected in the air instead of the ground data. OK, so in this part, we actually modified the algorithm a little bit. What we did was, we know from the ground algorithm that the error is 5 miles. So we run the ground algorithm, and it actually gives you a 5-mile error box. And then what we do is, we now can locate which transmitters you are actually talking to in some sense. So the RTLSDR, if there is a peak, then you can actually recover that this is the 99.3 in San Diego that must be transmitting because you're seeing this peak. And then what we do is we look at, we also know the details of the transmitter as well as the power received by the receiver. So we train a small learning model where we feed in the details of the transmitter and the received power, and it inverts that data into the distance. So we now know how far you are from each of these transmitters using a learning algorithm. So using a machine learning algorithm, we can just know what the distances are. And then we use these distances to intersect circles and regress circles and find out where you are in the country. And it turns out that if you do that, then this is what the benefit you get from aerial to ground. Remember, on ground, we were looking at 5-mile type errors with just received signal strength. And now you can get down to, on an average of 3,000 meters with just a test of. So here, what I'm doing is I'm splitting the data into test and train, like in typical learning algorithms. And I'm giving the system 5 examples of what the data looks like. And then the rest 25 examples, I'm going to ask it, tell me where you are. And this shows you the errors that you get when you give it 5 test examples, and then when you give it 6 test examples, up to 29 text examples, where we have actually 30 total data sets collected. And you can see that the error roughly goes to 3,000 meters, which is less than 2 miles. And the minimum error is pretty low. So it's 100, 200. Within 100 and 200 meters, you can get down to aerially if you're using this 20 megahertz band of just FM transmissions. This also shows that if you had data which was more than 20 megahertz, so we had transmitter data from only FM, but if you feed the system transmitter data for cell phones or other static transmitters, then pretty much you can get, I'm conjecturing that you can pretty much get 100 meters or 200 meters or even less than that if you just increase the total bandwidth that you are collecting. That is all I had. These are people who helped in this project. And
all right, let's thank our speaker. Are there any questions? Oh, we got one right there.
So in some areas, you see actually a lot of reuse of the FM frequencies pretty close together. Did you notice that, and did you handle that? Did that realize cause any problems?
Yes, very good question. So it turns out that reuse and illegal use is a big problem. So you drive through these places, and then it turns out that there are churches and there are places which are actually transmitting, which shouldn't be transmitting. and our algorithm automatically easily catches that. So you will see illegal activity right away, that this is a place where it's not supposed to be, and it's there. We did not, so there are places, so when we run the entire US simulation, there are places where there are problems like two transmitters are very close by that shouldn't be. We never got a chance to drive through there, and it might be that when we actually drive through there, you will get problems. So I cannot for certain say that we won't have problems in these areas, but there are problematic areas in the US that have this problem of very close towers that shouldn't be close. There are repeaters that are there that we have to take care of, and then there are repeaters that are not there. And so this whole simulation system took us some time to cook because there is a lot of case study that you have to do. Why is this happening? Why is that happening? And when you drive, then you find out that there is another problem. But yeah, I don't know if I answered that question. Thanks.
Any other questions? No? Okay, thank you very much.
Thank you.
All right, so we are going into a break. We will start back up at 3:15 for a little less than half an hour.